Are you also wondering if the channel loss equalization can be done by DFE only? The short answer is no. But in this video, I'm going to show the image of why not only apply the DFE in the equation. As discussed in the why not TXFFE or CTOE only video, most multi-protocol SerDes require equalizing the channel loss roughly 30 dB at the next rate. So in this video, that why not CTOE only video, we may only focus on the 30 dB case study of why DFE only don't work. Before any interesting images, let's understand the decision feedback equalizer DFE further. If the DFE makes the right decision, it not only cancels the reflection from the discontinuities, but is also away from the noise or crosstalk amplification. Although the residual ISI might be limited by the number of taps and depth resolution, this could be manageable. The most challenging is to cross the first tap timing, and we'll discuss that in detail. Please be advised that the decision feedback equalizer DFE must make the right decision to cancel the reflection or ISI. If the DFE makes the wrong decision, what happened? Does anyone want to guess it? Yes, that's correct. The DFE will introduce more ISI if making a wrong decision, and result in a burst error we call error propagation. Again, this error propagation might not be a big deal, but we must be aware of it over time. Lastly, the DFE cannot get rid of the precursor before the decision, so the residual precursor ISI will be a big issue, and we must get help from the TXFFE or the RXFCTOE if that's a big amount. After understanding the summary of the DFE, let's review again with a few waveform images to understand the DFE operation quickly. The single pass is feeding through a lossless channel and sample at the time TS. For multiple pass 1101 bit stream, there is 0 ISI at the data samples, which assumes the sampling point at the middle of the single bits, or I, to get the best timing margin for the data. On the other hand, if the single pass is feeding through a lossy channel with the first post cursor, which is artificial ISI, and the current bits may create a non-zero value at the next bit sample point TS1. For multiple pass 1010 or 1101 pattern, the data sample will be plus minus 0.5 or plus minus 1.5. So this will reduce synchronous sample swing or royalty margin, and then the samplers has a higher probability of making the wrong decision under the random noise. Please be advised that will limit the sampler's performance if the input dynamic range is big. What can we do? Yes, we need to equalize the swing of the data sample. The goal is to remove the problematic first post cursor completely by zero forcing, presumably in the single shot example. Once this was done, the multi-shot bit stream may get ISI free completely at the data sample again, even though there might be some glitch in the long run. The data sample one would be the same as the bit stream feeding through a lossless channel. Someone may notice that the single shot image shows a half UI delay applying the zero forcing, which is a closed loop delay of the DFE, includes the sampler's clock to Q delay, plus the feedback delay, plus the summing noise settling time. So, what is the maximum closed-loop timing delay we can tolerate? Think about your timing images for 5 seconds. Bingo! The allowed maximum delay is 1 UI. Everyone has a very good closed-loop delay image now. If the delay is past the 1 UI, the next data sample will sample the residual ISI 0.5. A lot of experienced engineers don't understand the 1 UI criterion well. So, this delay image should be very important for your DFE understanding. As we've known in the Y DFE video, the one-tap DFE is like a first-order IR except for a slicer. So, the DFE's response is a high-pass characteristic to equalize the channel's low-pass response. In addition, if the slicer, comparator, sense amplifier, strong arm latch makes the right decision, it converts the input analog signaling into the output digital full swing level. So, it has a noise or crosstalk immunity. But what happens if the slicer makes the wrong decision due to the input voltage margin was not enough? Bingo, that's correct. The DFE will introduce more ISI if making a wrong decision and result in a burst error. We call error propagation. Again, this error propagation might not be a big deal, but we must be aware of it all the time in the DFE design. Let's discuss the most common question is why don't we apply DFE only for a 30 dB loss? Think about your own images for 5 seconds. Let's look at the DFE's frequency domain characteristic. The smooth channel has the 30 dB loss at the next rate, and the one-tap DFE is the green one. Obviously, the one-tap DFE cannot equalize the channel well since the DFE's response is an inverse of the channel. What can we do? Any response image? Yes, we can increase the number of taps as shown here. More taps will have a low frequency boost, which would be more like the inverse of the channel response. For example, the blue 2 taps are better than the red 1 tap, and the green 3 taps are better than the blue 2 taps. If you are doing crazy 12 taps, the response is much smoother to be the inverse of the channel response, which could be close to the CTOE response. But we still cannot equalize that well and still need the CTOE's help. Moreover, more taps will decrease the bandwidth at the summing node by creating the extra device parasitic loading. Therefore, a longer settling time may not be able to cross the 1 UI DFE timing due to the self-introduced ISI. Let's look at the time domain with a single shot discrete time and the 30 dB response. The channel's frequency response of the 30 dB loss at the next rate will mainly have the blue first precursor and lots of red post cursors. The main cursor current bits is the green one. If we apply the one-tap DFE, then you will remove the first post cursor completely, but leave others as shown here. When we apply the PRBS7 bitstream into the one-tap DFE, we know the eye is still closed from the transient waveform. What can we do? How about 5-tap DFE? Which is the most popular number of taps people use? When we apply the PRBS7 bitstream into the 5-tap DFE, we can tell the eye could be open from the transient waveform. As you can see, there's a roughly 40 mV peak-to-peak differential opening. Okay, even though the 5-tap DFE only topology can cancel the 30 dB loss, it's not practical to leave the precursor ISI without the FFE or COE. From the power requirement, we must keep the number of taps as few as possible to reduce power. Please be advised that the power goes up quickly as a greater number of taps are used. We will show how the circuit image in detail to provide you more insight into how the clock, data path capacity, and data routing path sticker went up if more taps are added. The whole summing nodes loading would be another change if more taps are added. Therefore, we must go with enough taps without over-design. Again, for the long-tail postcursor, the DFE can handle by adding more taps, but that's not quite practical in power efficiency. Let's revisit DFE challenge of closing the first tap timing in one UI. As we know, the whole loop delay includes samplers clock-to-Q delay, feedback path delay, summing nodes sampling time, and sampler setup time. Take the 2-tap DFE as an example and assume the channels may only have 2 postcursors. To get rid of the 2 postcursors, both taps must meet the timing. As you can see, the input analog signal could be only 50 mV to 200 mV peak-to-peak differential, and the sampler's output would be full swing, which is also the input of the next tap. If we look at the difference between the first and second tap closely, we notice the difference is their sampler's clock-to-Q delay and their input swing. Please be advised that the sampler's clock-to-Q delay will decrease if the input swing is increased, and vice versa. So, the second tap delay will be only 20 picoseconds, since the second sampler's input swing is 1 volt digital level. So, the critical timing is the first tap. Another image for you is that the first samplers need to take the tiny input swing to convert or regenerate to the full swing by the positive feedback. Therefore, a simple delay image might tell you bigger input swing may take a shorter time to reach the full swing under the output. Therefore, we like to increase the input swing of the sampler to decrease the clock-to-Q delay and increase the first tap timing margin. Because of this, we favor having a CTOE as a preamplifier to boost the swing at the next rate for the 1010 pattern, and it helps the DFE's first tap timing a lot. Here is the summarized image you may have for why not DFE only in the equation. If a DFE only must equalize the loss up to 30 dB, then more TX output swing would be needed, but most specifications or circuit implementations only cover 800 mV or 1 volt at the most. On the other hand, for the 30 dB loss, the DFE will require more gain without dropping the swing too much at its input. Here is the system image from the TX to the channel and DFE output as a case study. The TX output swing is 1 volt, peak-to-peak differential, but after a 30 dB channel, the high frequency swing around the next rate could be only 30 mV with ISI. So the input I of the DFE or the output I of the channel is closed in the time domain. After a DFE, indeed, the input I can be opened up to 30 mV for the 1010 or clock pattern. Unfortunately, the 30 mV here has a side effect we've discussed, which is the sample's input swing sensitivity. With the 30 mV input, the delay could be 65 picoseconds or even longer, which means that does not cross the DFE's first tap 1 UI timing requirement in a real circuit image at 10 gigabit per second. Why is that? Any single shot image in your head? Bingo! This single shot image will tell you that the DFE's job is to cancel the post-cursor ISI, not the precursor ISI. In addition, the DFE does not amplify the signal at all. So, whatever loss you take from the channel, the signal swing will remain the same. So, what can we do? Yes, the CTOE can boost properly and has gain around the X-ray frequency. So, the CTOE's output swing or the DFE's input swing could be bigger to meet the sample's input sensitivity and reduce the first tap course timing easily. Again, in a realistic system budget, the CTOE may equalize up to 15 dB loss or slightly higher, and the DFE will take over rest equalization of the total 30 dB loss target. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with people who may be benefiting from it.